Welcome, everyone. I'm excited to kick off today's presentation. Today, we'll be exploring mechanical static equipment, pillars of industry. We'll cover the essential components, their importance, and how they support industrial operations. So, let's dive in and discover the vital role these equipment play in our industry. Welcome to our discussion on mechanical static equipment. First, let's clarify what we mean by static equipment. These are devices or structures that remain stationary during normal operation, meaning they don't have moving parts while they are functioning. Their role is fundamental. They serve as the backbone for containing, storing, processing, and transferring fluids in various industrial processes. Now, it's important to distinguish static equipment from rotating equipment. Static equipment, like tanks and pipelines, are fixed and do not involve any continuous internal motion. On the other hand, rotating equipment such as pumps and compressors are designed to have moving parts that transfer energy or fluids through continuous motion. Understanding this difference is crucial because static equipment plays a vital role in ensuring the safety, efficiency, and seamless operation of industrial systems. Without these stationary components working reliably, the entire process can be compromised. So, as we move forward, keep in mind how these static systems form the essential infrastructure that keeps industries running smoothly and safely. Let's take a closer look at pressure vessels. These are specialized containers designed to hold gases or liquids at pressures that are significantly different from the ambient environment. Their main role is to safely contain these fluids under extreme conditions, whether it's high or low pressure, elevated or reduced temperatures, or even corrosive substances. Now, because they operate under such demanding conditions, pressure vessels need to be stationary and built with robust structural integrity. Safety is critical here, as any failure could have serious consequences. That's why their design and construction are carefully engineered. When it comes to applications, you'll find pressure vessels everywhere, from chemical reactors and storage tanks for compressed gases like LPG, to heat exchanger shells, separators, and even boilers. They're fundamental components across many industries. Understanding their design involves a few core engineering principles. Mechanics of materials helps us analyze stress, strain, and deformation to ensure structural integrity. Fluid mechanics allows us to understand how fluids behave under pressure, which is essential for safety and efficiency. Thermodynamics is also key, especially for heat transfer, phase changes, and how temperature influences pressure inside the vessel. Material science plays a big role too. Selecting the right material, whether it's carbon steel, stainless steel, or specialized alloys, is crucial, as we need materials that can withstand the operating conditions, resist corrosion, and maintain ductility and strength at various temperatures. Moving on to design and construction considerations, we look at materials carefully, considering factors like maximum allowable working pressure, or MAWP, and the minimum design metal temperature, or MDMT. Other factors include corrosion allowances, fatigue from cyclic operations, and external loads. Standards and codes are fundamental. The ASME Boiler and Pressure Vessel Code, especially Section VIII, sets the strict requirements for design, fabrication, inspection, and testing. Industry standards like API 510 are also important. These codes are not just guidelines, they become law in many jurisdictions, ensuring a high level of safety and reliability. Finally, safety and maintenance are ongoing priorities. Common challenges include corrosion, fouling, erosion, and fatigue from cyclic operation cycles. Failure modes can be cracks, pitting, wall thinning, leaks, brittle fracture, creep, or even rupture. To prevent these, regular inspections, visual checks, and non-destructive testing methods like ultrasonic, radiography, magnetic particle, and penetrant testing are essential. Cleaning helps remove deposits and reduce corrosion risks, while repairs must always comply with codes, often involving welding or replacing parts. Monitoring is also vital. Real-time pressure, temperature, and vibration sensors help us keep a close eye on vessel integrity. Overall, Life cycle management ensures we can assess and mitigate failure risks throughout the vessel's operational life, maintaining safety and efficiency at every stage. Let's now take a closer look at piping systems, starting with an overview. Piping systems are essentially networks of pipes, fittings, and valves designed to transport fluids efficiently throughout industrial plants. They serve as the circulatory system of these facilities, moving everything from raw materials to utilities needed for operations. When we talk about the key role of piping, it's all about ensuring the continuous flow of materials and utilities, which is critical for maintaining smooth processes. These systems are static conduits, meaning they don't move, but their design and interconnectivity are vital, especially since many processes depend on uninterrupted flow. Now, looking at their characteristics, piping systems are interconnected networks that are essential for continuous operations. They handle a variety of applications, like process piping for chemicals, crude oil, and refined products, utility piping for steam, compressed air, water, and inert gases, as well as long-distance pipelines transporting oil, gas, and water across vast distances. Understanding the principles behind their design is crucial. Engineering principles such as fluid mechanics help us analyze flow dynamics, pressure drops, and friction losses. Stress analysis allows us to ensure pipes can withstand internal pressures, external loads, and thermal expansion or contraction. Thermodynamics plays a role in managing heat transfer within pipelines, and material science ensures the materials used are compatible with the fluids, can handle the operating temperatures, and resist corrosion. When it comes to construction, choosing the right materials, like carbon steel, stainless steel, alloy steels, or plastics, is key. Considerations such as pipe sizing, pressure and temperature ratings, flexibility, and proper support spacing are all critical. We also adhere to established codes and standards, like the ASME B31 series, API, and ASTM standards, to ensure safety and reliability. Compliance with these standards helps prevent leaks, environmental hazards, and maintains operational integrity. Moving on to challenges and maintenance, corrosion, both inside and outside, is a common issue, along with erosion, fouling, scaling, vibration, and fatigue. Failure modes can include leaks, ruptures, cracks, wall thinning, or joint and support failures. Regular inspections, including visual checks and non-destructive testing like ultrasonic or radiographic testing, are essential for early detection. Corrosion management techniques such as coatings, cathodic protection, and inhibitors play a vital role. Cleaning methods like pigging and chemical cleaning keep pipelines clear, while repairs must be performed with code-compliant welding and material replacement. Leak detection involves routine patrols and advanced sensing technologies, and overall integrity management requires proactive risk assessment and mitigation strategies. In essence, maintaining piping systems is about ensuring safety, reliability, and efficiency, key factors that keep industrial operations running smoothly. Now, let's take a closer look at above-ground storage tanks, or ASDs, which are a fundamental part of many industrial facilities. These tanks are large containers designed to store liquids, sometimes gases, at or near atmospheric pressure, and they are positioned above ground for easy access and maintenance. Their primary role is bulk storage of raw materials, fuels, chemicals, and water, making them vital for operations across various industries. ASDs are static structures that are clearly visible and accessible, which simplifies inspection and maintenance. Many of these tanks have secondary containment, a safety feature that helps prevent environmental spills in case of leaks. You'll often find ASDs in refineries, chemical plants, water treatment facilities, and fuel terminals, highlighting their versatility. When it comes to design, several engineering principles are key. Structural engineering ensures these tanks can withstand hydrostatic pressure from the stored liquids, as well as external forces like wind and seismic activity. Fluid mechanics help us understand the pressure exerted on the tank walls and bottom, which influences venting and safety measures. Material science guides us in choosing materials that offer the right strength, resistance to corrosion, and suitability for the temperature of the stored product. And if the stored liquids are heated or cooled, heat transfer considerations become important. Most ASDs are made from carbon steel, though stainless steel is used for specialized or corrosive products. There are different types of tanks, including fixed roof tanks, like cone or dome-shaped roofs, and floating roof tanks, which can have external or internal floating roofs to manage vapor emissions effectively. Design considerations include shell thickness, roof structure, foundation stability, nozzle placement, and venting systems. Compliance with standards such as API 650, API 620, and API 653 is essential to ensure safety and reliability, along with adherence to NFPA and UL codes. Safety cannot be overstated. Proper design and maintenance are mandatory to prevent spills and protect both personnel and the environment. Moving on to challenges and maintenance, corrosion is one of the most common issues, especially at the tank bottom, which can lead to leaks if not addressed. Foundation settlement or overfilling can also cause structural problems. We need to regularly inspect these tanks visually and internally, following standards like API 653, and use non-destructive testing methods such as magnetic flux leakage or ultrasonic testing for critical areas. Corrosion protection measures, like coatings and cathodic protection, help extend tank life. Cleaning out sludge and sediments ensures the tanks remain operational and safe. When repairs are needed, welds must meet code requirements to ensure integrity. And of course, secondary containment systems, like dikes or berms, must be regularly inspected and maintained to contain any potential leaks or spills. In summary, ASDs are a critical component of industrial storage, requiring careful design, diligent maintenance, and strict safety standards to operate effectively and protect our environment. Now, let's take a closer look at the static equipment distribution within a typical process plant. As you can see, piping systems form the vast circulatory network that connects everything together. They're essentially the veins that carry fluids throughout the plant. On the other hand, vessels and exchangers act as the heart of the process there, where the key reactions and heat transfers happen. This chart here provides a proportional breakdown, giving us a clear idea of how these components are distributed in a standard setup. Understanding this distribution is crucial because it helps us optimize plant design, maintenance, and operation. It's a great reminder of how integral both the piping and the static equipment are to the overall process flow and efficiency. Now, let's take a closer look at the typical design pressure ranges for static equipment. As you can imagine, these vessels are built to withstand tremendous stresses. The key point here is that pressure vessels are specifically designed for high pressures, unlike atmospheric storage tanks, which operate under normal atmospheric conditions. This difference is crucial because it influences the materials we choose and the safety standards we follow. Understanding these pressure ranges helps us appreciate the engineering challenges involved and the importance of designing equipment that can safely handle the pressures they encounter during operation. This is a fundamental aspect of ensuring safety and reliability in our systems. Let's take a closer look at the primary causes of failure in reliable, static equipment. Even though this equipment is designed to be dependable, it's important to understand that it's not completely immune to issues. One of the most significant threats we face is corrosion, which can be particularly problematic in piping and vessels. Corrosion can gradually weaken the material, leading to leaks or even catastrophic failure if not properly managed. That's why robust inspection and maintenance practices are so critical. Regular checks can help us identify early signs of corrosion, allowing us to intervene before serious problems develop. This highlights the overall theme that proactive maintenance and diligent inspection are essential to maintaining the integrity and safety of static equipment over time. Now, let's take a closer look at the key risk and performance factors. As you can see, different equipment types present unique challenges. This radar chart here helps us compare these key factors visually. What stands out is how vessel failure tends to have a very high impact, meaning that when a vessel fails, the consequences can be quite severe. On the other hand, fired heaters, while also critical, tend to carry high costs associated with their maintenance and operation. This comparison really underscores the importance of understanding the specific risks tied to each piece of equipment. It's crucial for us to prioritize our risk management efforts accordingly and ensure that we're addressing the most impactful factors. Remember, understanding these differences helps us improve safety, optimize performance, and control costs across our operations. Thank you for joining me for this final slide. So in conclusion, I want to emphasize the key points we've discussed today. First, we explored how implementing these strategies can significantly improve our efficiency and outcomes. It's important to remember that consistency and commitment are essential for success. We also looked at the challenges that might come up and how to overcome them with the right mindset and tools. Most importantly, I want to highlight that these concepts connect back to our overall goal of continuous improvement and innovation. By applying what we've covered, we can create a more dynamic and resilient organization. So, I encourage you to take these insights and turn them into action. Remember, progress is a journey, and every step counts. Thank you for your attention and dedication.